Hi, my name is Vasco Cardoso. I'm a master student from the Universidade de Coimbra in Portugal, and I'm working on my master thesis in the Universidad de Alicante about the collisional evolution of the Jupiter Trojans. So the Jupiter Trojans are small asteroids that orbit the Sun in these stable regions called L4 and L5, which are the Lagrangian regions of Jupiter. These have become an interest topic of study over the last decades, because according to the NIST model, they were captured from the transplanetary disk, the original transplanetary disk. But apart from the stability on their orbits, there is some evidence that tells us that they have undergone some collisional evolution, and this evidence is the now identified 6 asteroid families, such as the Eurybates, Archicelaus, and Animals. So in this work, what we aim to do is to understand if the Jupiter Trojans and the Kuiper Belt objects come from the same primordial disk. So to do so, we have to test our code against some of the previous collisional models on this population, the Jupiter Trojans, such as the Lien-Bernini from 2007 and Marshall 2022. So the first one takes as the fragmentation model based on Petit-Farinella, which is actually the same one that we used to, but they also take into account the work of O'Brien and Greenberg that showed that the general shape of the final evolved asteroid population is determined primarily by QD, which is the specific energy required for disruption, but also variations in QS, which is the specific energy required for shattering, and FKE can affect such final population even if QD is held the same. So basically QD and QS are different from each other because QD takes into account the reaccumulation of fragments into the bigger body after the collision, while QS doesn't. And the relationship between these two parameters is not so clear. So if we were to take a scaling law of QD, such as the Benson-Aspog, this one, we can reformulate it to this form, and by changing the parameters C2 and lambda 2, we can create a family of QS scaling laws that underneath the QD gravitational regime. The gravitational regime is the regime in which gravitational effects are most significant. Gravitational effects such as reaccumulation of the fragments into the larger body. So after creating the QS, we have also this other parameter, E, which is tells us how much of the energy from the collision is into kinetic energy of the fragments, and the two combined create the corresponding QD that would have the same effect. So we also studied the case of Marshall 2022, both from Morbidelli, and use a fragmentation input that is different from ours. It comes from smooth particles and picographic conditions from the 2025. So actually, to simulate the Jupiter population, we used a more simplified version of the Alicante code to track on the evolution of the single zone. Then we use the fragmentation model by Farinella, as I told, but adapted to include the new scaling laws following the Lien-Bernini. But for the and for the evolution, the evolution model, we actually use the typical procedure. So these are the cases that we took from the work of Delia, the actual same QS cases. And these are the results that we got from them. So these are the results come in the form of cumulative size frequency distributions. So which means that in the y-axis, we have the number of bodies equal or larger to a given diameter, while in the x-axis, we have the diameter of such body. By looking at these plots, we can see that our results pretty much are acceptable according to their work, and that our model can reproduce them. So we, given this, we try to make the same procedure for the work for the scenario that Marshall 2022 proposed. And so they use a weaker scaling law. And so, which is in this solid line, we tried with some different QSs that go under this scaling law. These are two cases. And then these are the results that we got. As you can see, we were able to reproduce the same deep feature and although it doesn't have the same accentuation, but this is mostly because the fragmentation code that we use and theirs is quite different. And so, having tested our model, we then try to explore a scenario of our own, in which we took the scaling law that Marshall proposed, and we scaled it up and down, therefore creating stronger and weaker bodies. And then for the evolution of the population, we took a portion of the population collisionally evolved from the transplanetary disk at the beginning of the dynamical instability. What this means is that, so basically we started by evolving the transplanetary disk until the instability of the giant planets, in which then Neptune penetrates this disk and ejects bodies both outward and inward. Both of some of the bodies that are ejected outward are we now know as the Kuiper belt objects. We also simulate this population, but and we got some really good results according to the observations, but this isn't the topic for another talk. So I'm going to focus more on the Jupiter Trojan population. So some of the objects that were ejected inward were captured by Jupiter, and these are the ones that we actually evolved under the conditions of this population. So these are the results that we got. And so again, a cumulative size frequency distribution. And so in this case, we have two initial populations that are different from each other according to the slope of the smaller bodies in the initial population in the transplanetary disk, which are in dotted lines. And then it's in solid lines, we have the actual evolved populations. And then in black, we have the observed populations population of the Jupiter Trojans. This is the case for the stronger scaling law, so stronger bodies. And we actually understood that a dynamical instability at 20 million years would be the best scenario. We actually tried with some other slightly different instability times. So this is the nominal case. And then we have the case for the weaker bodies, in which, as you can see, there is a pretty good match between the observed population and the case of alpha equal 0.4. So what we concluded from this was that by taking this initial population in a transplanetary disk, we were able to reproduce both the final population of the Kuiper belt objects and the Jupiter Trojan population according to our model, of course. So we further extended our research. Marshall 22 also proposes what would be the best impact conditions to form the Eurybates family, which is one of the Lucy targets. And so what we did was we actually put our calculating what would be the probability of formation of this family according to our own scenario. And what we got were pretty low probabilities, actually. So then they also present the number of craters in the surface of the main body of the Euribates family, Euribates. So the number of, which are the red dots. So we have the number of craters bigger than 1 kilometer and then 10 kilometers. So we try and do the same under this, and this is the number of craters for kilometers squared. So we tried under the same conditions, we reproduce a more detailed version of this data. So we have into account all of the diameters. And as you can see, we come pretty close to their number of craters. But when we actually evolve, use our own scenario, we got these blue lines, which are always above the other results. So, and as you can see, a weaker scaling law, which is the solid line. So the weaker the scaling law, the more craters are created in the surface of this body. So we actually did the same for other Lucy targets, such as Lucas and Patroclus. The same tendency, the same tends to happen. And then for Polymele and Horus, the same thing happens. And so what we can conclude from our model, it's that it produces similar results to other published models. Then combining both scaling law approaches could help establish a relationship between QD and QS. And that based on our simulations, we have found evidence that supports the theory that the Kuiper belt and the Jupiter Trojans originated from the same outer disk. We also predict the crater size frequency distribution for Lucy targets, and we show a low probability of forming the Euribates family under the impact conditions claimed by Marshall 2022. Thank you.
¿Preguntas? Question. Are you thinking about extending this analysis to other asteroid families? Not just the Trojans, other collisional families?
Populations. Right now we're just because this was all very experimenting. We're trying with different scaling laws, different initial populations. So we also, as I said, we also simulated the Kuiper belt objects. And for now, just this, and try and reproduce these smaller features like the families and the craters is now our main goal. Yeah.
Thank you.